Iniciar a próxima aula. I have an introduction. Good afternoon. My name is Guilherme Pereira. I'm a professor here at the Department of Electrical Engineering. And I'm glad to be here to introduce the next speaker, that's Professor Vijay Kumar. Professor Vijay Kumar is the UPS Foundation Professor at the University of Pennsylvania, in the United States. He has been professor at UPenn since 1987, where he has appointments in the Department of Mechanical Engineering and Applied Mechanics, Computer Information Science, and Electrical and System Engineering. Professor Kumar served as the Deputy Dean for Research in the School of Engineering and Applied Science, as the Director of the GRASP Lab, one of the most important robotics laboratories in the world. He is also the chairman of the Department of Mechanical Engineering and Applied Mechanics and the Deputy Dean for Education in the School of Engineering and Applied Science of UPenn. More recently, Professor Kumar served as the Assistant Director of Robotics and Cyber Physical Systems at the White House Office of Science and Technology Policy. Professor Kumar is a fellow of the American Society of Mechanical Engineers, a fellow of the Institute of Electrical and Electronic Engineers, and a member of the National Academy of Engineering. Professor Kumar's research is in the area of robotics, especially multi-robot systems and the micro-aerial vehicles. Professor Kumar's group works on creating autonomous ground and aerial robots, designing bio-inspired algorithms for collaborative behaviors, and on robot swarms. Professor Kumar is the recipient of several awards, including Best Paper Awards of very important conferences such as DARS, ICRA, and RSS. Today, Professor Kumar will show us part of his very exciting work. So before we start this lecture, I'd like to say other things. All these things I mentioned, I forget to say that Professor Kumar was my thesis co-advisor 11 years ago. In that time, I wrote in the acknowledgement of my thesis the following. Professor Vijay Kumar was extremely important, not only for the conclusion of this thesis, but also for my development as a researcher. The short time we have worked together will certainly influence my whole scientific life. Only today I can affirm that this is really true. And Professor Kumar also had important influence in the formation of other Brazilian professors that are here today. So, I believe he has strongly influenced the robotics in Brazil. But because of this, I'll call now to this stage some people that are here: Professor Mário Campos, Professor Luiz Chaimovics, Professor Luiz Denilson Laudares, Professor Valdir Grassi, Professor Pedro Chiroma, and Professor Luciano Pimenta, that will also say something here, and will present Professor Kumar with a gift for this importance in our lives. I will give you the word to Professor Mário, that will talk something here.
Okay. So it has been quite a few years. So you come to the light. You just It's been quite a few years. Too many for me to actually say it in public. But young Professor Vijay Kumar arrived in the scene of GRASP Lab and rescued me in my PhD dissertation. So somehow what we have here is some like first, second, and third generation. And we all, right, want to present Professor Vijay Kumar with this simple token of appreciation, and we read that for you. It says, presented Professor Vijay Kumar, in appreciation and recognition of your outstanding contribution and continued inspiration for the academic careers of your Brazilian friends. September 21st, 2014.
So finally, we will start the lecture.
Okay. Thank you so much. This is such a kind introduction and such a generous welcome. As Guillermo and Mario said, I have many years of a close association with people in Brazil. What they did not say is that I actually own jerseys of the last two number 10 players that played for the Brazilian soccer team. Neymar, Ronaldinho, and also Ronaldo jersey. In spite of that, they didn't win, but that's a different story. But really, we just took this picture outside. I didn't know that we were going to come up on stage, but we've written many papers with these guys, and they've really also influenced the students in the lab and the research we've done, and for that I'm grateful. So I'm really glad to be here. First, I've been many times to Brazil. It's the country that's near and dear to me, and there are so many people that are close to me, and then finally just an opportunity to tell you about the work we're doing. So I titled this set of lectures, Aerial Robot Swarms, but this is not really a research talk. It's more a tutorial on how we approach the problem of creating swarms of aerial robots. And in the process, I'll go through a lot of the material we cover in our graduate level robotics class. So I hope this will be accessible to everyone. And if you have questions, please do interrupt me and ask questions. So let me get started. It's actually a dangerous place to stand. So let me get started by telling you about what I wanted to talk about. So first, I'll tell you a little bit about micro-aerial vehicles and their applications. Most of the talk is about modeling these vehicles, thinking about the dynamics, how to control them, and how to plan motions for micro-aerial vehicles. And then an important part of the problem is actually having these small vehicles understand where they are in the environment. So localization, estimation of position and velocity is a key research challenge. And I'll tell you about some of the experimental techniques and the theoretical tools we teach in class. And then finally, some systems questions. For micro-aerial vehicles, there are the so-called SWAP constraints, SWAP, size, weight, and power. So things that you can do with a Boeing 747, you cannot do with micro-aerial vehicles just because of the size. So I'll tell you a little bit about that today. So this is sort of part one. And the second part tomorrow, one of the things, and I'll motivate this a little bit today, is we're now switching to camera-based estimation techniques. So I'll tell you a little bit about how we do that, how we think about vehicles cooperating with each other onto swarms and some of the applications. But let me first start by talking about micro-aerial vehicles and their applications. So the most important thing I want you to realize is that vehicles on the right-hand side, these are mostly military vehicles. These are not autonomous. They're mostly operated by operators on the ground. So these are things that we're not particularly interested in. So this is all fairly standard technology going back at least 20 years. The excitement, at least in research, is really on vehicles that are much smaller, vehicles that operate indoors, vehicles that can go through doors, and vehicles that may weigh at most 1 or 2 kilos. So that's what we mean by micro-aerial vehicles. And we use these vehicles for applications in search and rescue. So this is a vehicle of ours operating in a collapsed building. Actually, it was the electrical engineering building at Tohoku University in Sendai, 2 months after the earthquake in Fukushima in 2011. And this vehicle was able to go into areas where humans could not go and ground robots could not go. We're interested in applications in security and first response. So what you will see here is one of my students, Kartik Mota, operating with the screen. He's commanding these vehicles. So you see this building here. He's essentially telling the vehicles to go surround this building, and the vehicles decide which vehicle goes to what part around the building, and essentially they're monitoring the area around the building. The interesting thing about this is that Karthik interacts with the team, but not with the individual vehicles. The formulation we use, the operator is agnostic, is unaware of the number of vehicles in the team. He doesn't care about who does what. He just tells the vehicles a high-level task, and then they organize themselves and determine how to execute this task. So each vehicle is essentially feeding back video streams like the one you see here as they travel. And at the base station, these videos are mosaiced together so that you have a coherent picture that the operator can then see. So if there's a terrorist attack or a disaster, that is a terrorist attack. I got it.
Oh, okay.
It's just,
So take a while.
that's what one of our vehicles sounds like. Why is that is that feedback?
Take this blood out of the
This
sound.
one.
Not these. You really need these?
Okay, take it out. All right, we'll do it without sound. So this is mostly concerned with overhead flight, but what we really want to do is to create the next generation of vehicles that essentially fly inside buildings. So here you can see real-time video coming from one of our flying robots. So this robot is not autonomous. It's actually being joysticked by a human being. Actually, there are pieces of this video that are driven autonomously, but this particular piece is driven manually. But what we'd like to do eventually is to make all of this autonomous. So this segment, by the way, is autonomous. So we can tell the robot to go down a hallway, and it'll do it without any joystick control. But for the most part, these maneuvers are hard to do today with just autonomous control. It has to be controlled by a human. And eventually, we'd like to make this autonomous. And again, for smaller vehicles, the only sensor that really scales with the size is a camera. So if you look at your smartphones, cell phones, most of you have 2 cameras on a very small package. So if we can take information coming from those cameras and make it so that the robot can essentially understand the environment enough to navigate it, that would be our high-level goal. There are many spin-offs in this area. The one that we work most closely with is KML Robotics, and I'll tell you a little bit about the work we're doing with them. One of the things they're doing independently is developing these hex rotor platforms for aerial photography, along with a Chinese company called Unique. And I'll show you a little bit about the work that we're doing inside dams. So one of the things we'd like to do is to inspect structures like this. So this is Carter's Dam near Atlanta, Georgia, in the US. And we're doing this with the US Army Corps of Engineers. So if you want to inspect, for example, the structural elements of this dam, look for bolts that might have sheared off or columns that might have rusted. We want robots to do that. And one of the interesting things about this is if you want robots like this to operate autonomously outdoors, in fact, there's very little GPS available in the shadow of these buildings. So our robots essentially use onboard sensors to create maps of the kind that you see here. So this is one of the maps that it's creating, and you can see what the robot actually sees. And the key thing is that it's able to localize based on information that sees what it sees and based on the map that it's building. One interesting challenge for us is to actually go inside the building. And I'm sorry, this picture doesn't come out well, but this is a penstock. So a penstock is this large tube, typically 20 feet or so in diameter, that delivers water from the reservoir up there down to the turbines at the bottom. And so this tube is at a 23-degree angle, and it's a big black tube. And if you want to inspect it, there's no way a human can actually climb up the tube. In fact, what they do is they build scaffold, they build structures, and it's a very tedious job to inspect this structure. What we can do, on the other hand, is take this robot and actually fly right up this tube. You can see this is actually the water coming down, a little trickle of water coming from the top because the valve has not been closed completely. But essentially, we want to be able to navigate all the way up and look for corrosion spots in this tube. And then lastly, one area we're very interested in is precision farming. So what you see here is our aerial robot in an apple orchard. And we're from the University of Pennsylvania, but it turns out there's another university that's close by which has which works on agriculture problems. So we collaborate with them. So our robots are able to build maps of these orchards, count fruits, tell the farmers the health of every robot. So here you'll see the orchards, and you'll see a robot flying autonomously between the rows of trees. And they also build maps like this. So these are infrared maps of these plants. This is a map of something called NDVI, the Normalized Difference Vegetation Index, which tells the farmer something about the health of the plants. It can also build 3D models, and these models are good for estimating the size of each plant. And you can see it can fly on top and along the sides to build these 3D models. And in a minute, you'll see there are two other robots that are also doing the same thing. So if you want to cover large areas very quickly, you can see that these three robots together can cover this whole orchard and tell the farmer which trees need attention, where you need to fertilize, which trees need water. As you all know, water is a big problem, not only here, but also in the US. And if you can optimize how much water you're using, that would be something that would greatly economically benefit farmers and also save natural resources. So the kinds of vehicles you might use, there are many alternatives. The most obvious one are fixed-wing vehicles. But when you're operating in indoor environments, so imagine again in search and rescue or law enforcement, it's very hard to have small indoor vehicles that can quickly zip around because unless you know the entire environment perfectly, and unless the environment is not cluttered, in other words, there are very few obstacles, it's very hard to take a fixed-wing aircraft and have it fly autonomously. You want the ability to come to a sudden stop and hover if you see obstacles that you had not seen before. So these don't represent a very good alternative. On the other hand, flapping wing aircrafts, which resemble birds or insects, actually have a great deal of promise. So there are two types, one that mimic birds and one that mimic insects. So the insect-like vehicles essentially mimic helicopters. Instead of having rotors that helicopters do to hover, the avian flight type vehicles flap their wings, and they're able to hover by just flapping their wings. And there's a very nice prototype called a Nano Air vehicle created by a company in California called AeroEnvironment. So that's sort of the state of the art. But the problem is that if you want to control something like this, to understand the unsteady flow that you have at these length scales, and then to create dynamic models, and then invert them for autonomous control, today is very hard. Another option is to go with rotorcrafts, and there are many versions of this. So the helicopter is the simplest one that we're all used to seeing. The ducted fan is a variant of this. The idea in a ducted fan is you have got a propeller that's essentially forcing air through ducts, and the ducts can be oriented differently to change the direction of thrust. You can have rotors that are arranged coaxially and rotating in opposite direction. You can have 4 rotors, as I'll show you in a minute, or 6 rotors. And here's a picture of a coaxial robot, and here's a hex rotor robot. Our preference actually is to work with quad rotors. And if you want to build a swarm, you want to make sure that individual units are as simple as possible. So think about a quadrotor. I'm a mechanical engineer by training. If you think about the design, there's nothing simpler than this. It's basically a rigid frame, 4 motors, 4 motor controllers, 4 props, and then some electronics. There are no moving parts like in a helicopter. There are no hinges. There are no flapping wings. It's very, very simple to make. And you can make lots of these very easily. So our preference is to work with these. And the way we think of this is in this pyramid of robots. On the top are the military vehicles. They cost a lot of money, and there are very few of them in the world. There's maybe 740 or so drones, as they call it, that we have today in the world made by the US. There might be other countries making others, but very few of these. And they cost a lot of money. And from the standpoint of what we do in the classroom or the laboratory or research, they're completely uninteresting. So at the other end of the pyramid, you see what has made cell phones, cameras, and so on really inexpensive. Better processors, better sensors in large volumes, and many of these are very, very inexpensive. So there are millions of these that you can buy, if not billions, and the unit cost is very small. So that's why we have inexpensive toys. So if you look at the toys that you have today and compare it with the toys that your parents had, right, your toys are much better and they're less expensive. I guarantee you that. And that's why you have hobby kits. So your parents or your professors never had those hobby kits when they were your age. And that's because all of this stuff is really inexpensive. So rather than reinvent new sensors, new platforms, we can think about how to take our knowledge, what we learn in the classroom, and what we develop in the laboratory, which is really this, and how to leverage all of this and instead turn it around and make these vehicles autonomous and make them do useful things. And this is really the focus of our laboratory. So what you're going to hear in these 2 lectures is not about how to build hardware. We assume we can get hardware off the shelf. If you have better hardware, you'll be hard-pressed to make 100 copies of this so that I can build 100 robots. It's just very difficult. So you might as well use what's in your cell phones, what's in your cameras, and try to work with those. So that's our philosophy. So that was really my brief introduction. Are there any questions before I move forward? I'm going to pause at least 5 times and see if there are any questions. And if I don't get any questions, I'll just stop. I'll stop speaking. So this is your chance to ask questions while I grab some water. Otherwise, I'll start asking you questions. Yes?
You mean your research based more or less in off-the-shelf technology. But when we start thinking about technology and vision, and so this, you come to some point that are not so straight out of the shelf.
Absolutely. So it would be a mistake to say that we do research based on off-the-shelf technology. All I'm saying is that the hardware that we buy has got to be inexpensive, easy to use. If you don't do that, if you build your hardware for research, then you are putting a research problem in the path of another research problem. And that other research problem will never get solved, right? So our focus is over here, and all I'm saying is that we'll take whatever is available today in the market. And hopefully it's less expensive than what we can build in the lab and equally functional. Okay? Yes?
Considering the cost of an individual robot as an important aspect of swarming applications, what is your opinion regarding the use of free robotics, multi-rotors with the fixed halt flight controller blocked partially by ETA slurry, as an alternative to the more expensive scanning technologies, multi-rotors?
So we'll come to that. So this is a dangerous place to stand. We'll come to that in a minute. So I want you to hold this question. I'll show you the robots we're working with, and I'll tell you why we're using the ones we're using, and we'll come to that question. Okay? So let me move ahead and tell you a little bit about our approach to modeling these robots and how do we do dynamics and solve control problems. So again, I'm going to talk about quad rotors. You can apply similar approaches to other kinds of vehicles as well, but what I'm going to be talking about is mostly tailored towards four-rotor aircrafts. So just to set some notation, you have, again, four rotors. Each of these has a speed omega 1, 2, 3, 4. You typically have an inertial frame, A1, A2, A3, a body fixed frame, B1, B2, B3, and we work with homogeneous transformation matrices, or those of you who know about group theory, you can think of these as elements of a Lie group that do the transformation from the inertial frame A into the inertial frame, into the moving frame B. So that's some basic notation. Euler angles are a good thing to use in this kind of a setting, and our Euler angles are somewhat unorthodox. So our first Euler angle is the yaw. So you take the inertial frame A1, A2, A3 and rotate it into E1, E2, and E3. So that gives you that. The second one is actually the pitch, which is the angle phi, and that gives you this red frame. And then the third one is roll, which I haven't shown here, but that's the angle theta. So those are the three angles we work with. Of course, roll, pitch, and yaw representations have singularities. So at the back, we're actually doing all the computations using rotation matrices that have no singularity or quaternions. We prefer rotation matrices. Another way of doing it is actually using quaternions. But basically, our representation is the z, x, y sequence of Euler angles. Again, yaw, pitch, and roll. And there are singularities. But at the back of the computations are actually being done using rotation matrices. So in terms of control, the big challenge is you're trying to control position. You're trying to control 3 orientation variables. But you only have 4 inputs, which means the system is underactuated. So from a control standpoint, that's the challenge. And to see this, you can see that roll and pitch are quite easy to control. So if I want to roll the vehicle, all I have to do is increase the speed of one of the rotors, and I'll get more thrust, and that'll cause the vehicle to roll. And the same thing is true if you want to roll the other way. And you can generalize this for pitch as well. But translation is a little harder. If I want the vehicle to go from one position to another position by just going sideways, this is hard to do while staying horizontal. The only way of doing it is you got to pitch forward, and then you have to accelerate, and you do that by increasing the thrust. But then when you're going at full speed, you realize you have to slow down, which means you have to pitch the other way, and you have to direct the thrust in the opposite direction. So you have to decelerate, and then when you come there, you have to essentially pitch back to the right orientation. So this is a complicated sequence of maneuvers, one that involves using rotations as a way to do translations. In many vehicles, that is not the case, right? But in underactuated vehicles, that's the only way of doing it. So how do you deal with these underactuated systems? So we have 4 inputs, and we have 6 things we're trying to control, but we only control 4 things, and those 4 things are the position and yaw. So in terms of input and output variables, these are the inputs, and those are the outputs, position and yaw. We don't worry about roll and pitch. They're not explicitly controlled, but as you will see, they're implicitly controlled. So again, U is the input, and Y is the output, and each of these input variables essentially controls the amount of thrust you apply in each rotor, and the thrust goes as the square of these inputs. So the thrust is proportional to the square of the RPM. In addition, you also get drag forces. So these are moments. So anytime I try to spin a rotor like this, there'll be a drag moment in the opposite direction, and that also goes as the square of the RPM. Right? And you'll notice that 2 of the blades are pitched one way. The other 2 blades are pitched the opposite way. So here, a counterclockwise rotation produces an upward thrust. Here, a clockwise rotation produces an upward thrust. So the effect of the inputs is to produce a thrust and a moment. The moment is a drag moment, but what we consider instead is the drag, opposite of the drag that acts on the airframe. So this combination of forces has somehow got to take these inputs and be able to control those outputs. So there's equations you can write, and these are very, very standard equations, the Newton-Euler equations. The first 3 equations are essentially the Newton's equations. The acceleration is given by the gravitational force, except the gravitational force is in the inertial frame, and we rotate it back into the body fixed frame. The thrust, which is proportional to the omega squared terms, is added up. That's the coefficient. And essentially, this is the acceleration in the body fixed frame. The next set of equations is the angular acceleration, again written in the body fixed frame, where I is the inertia tensor for this. The inertia tensor is usually taken to be diagonal. You can position the coordinate system so it's diagonal. These are the nonlinear terms that depend on the square of the velocities. And again, these are the moments. So you'll notice that in this particular row, there's a positive term and a negative term, which means rotor 2 and rotor 4 essentially allow you to control the x direction motion. So this is the x direction motion. By changing omega 1 and omega 3, I can essentially control this pitching motion. Likewise, by controlling omega 1 and omega 3, by controlling omega 2 and omega 4, I can control the pitching motion. By controlling omega 1 and omega 3, I can control the roll motion. And the last row allows us to control the yaw. So there are basically 4 things you're controlling here by these omegas. One is the effective thrust in the B sub z direction, and then the effective moments along x, y, and z. So those are the 2 inputs really you're playing with. I can say it's the omegas, but practically it's the f along the z direction and the total moments. So to get some intuition, let's think of everything in the plane. Right? This makes life a lot easier. So if I were to do things in the plane, now this is the YZ plane, the B1, the B2, B3 plane. Those equations simplify a lot. So if I write down the simplified equations in state space, I get this. Now there's only 2 inputs. U1 is the net thrust in the B3 direction, and U2 is the net moment in the phi direction. Right? So again, now there are 2 inputs, and there are 3 things we'd like to control, y, z, and phi. So this problem is a little easier to understand. Are there any questions about the model? No questions? I'll give you a copy of the slides. You don't have to take pictures. I'll give it to you guys. You can. You're welcome. So systems like these are called, they're nonlinear. So again, they're nonlinear because of the sines and the cosines. But they're not completely nonlinear. They actually have some structure to them. And these systems are called affine. So if you look at the state, which is this, the derivative of the state, you have one term followed by another term times u. You're actually linear in u. Right? Because of that, it has this structure in Sapphire, and the outputs look like this. So there's some standard tricks you can play. And I'd like to tell you about two strategies we use. First is a linear strategy, and the second is a nonlinear strategy. So let me tell you about linear controllers first. So in linear controllers, we start first with the z direction. We figure out how to control the z direction, then the y direction, and then the angle. So in the z direction, this is what you're faced with. Essentially, it's the second row. You linearize about the hover configuration where the pitch angle phi is close to 0. Well, if the pitch angle phi is close to 0, cosine of phi is equal to 1, and you get this equation. So that's the operating point. If u1 equal to mg, the acceleration in the vertical direction is 0. So essentially you're essentially linearizing about this point, phi close to 0, and u1 equal to mg. So if you want your errors to go to 0, you simply let your system error behave according to the second order differential equation. In other words, if this were true, then you know if these two guys are positive, that the difference between z desired and z will go exponentially to 0. So how do you make this happen? Well, you simply plug in the value for u1 given by this. So remember again that phi is close to 0, which means cosine phi is 1, so you're dealing with this differential equation. So if I take this and I plop it into u1, I'll essentially get this. So just in the vertical direction, I can drive the errors to 0 without any problem. Next, the horizontal direction, the y direction. Again, at the hover configuration, if I try to look at this equation, sine phi is close to phi, so that equation simplifies. I have a linear equation. So the problem here is I don't have an input that can be used to drive y double dot, because my u1 was already used to drive z to its desired value. So I have no input here. So how do I control y? What input can I use to control y? Well, I have phi, which I can change, and that's the only way to control y. So if I look at this equation, and if I want the errors in y to decay exponentially to 0, I can figure out what phi should be. In fact, if I can make phi to be equal to this quantity, and if I substitute this back in here, that'll guarantee that this will go to 0. Which means in order to control the horizontal position, I have to be able to set phi to this desired value over here. Got a question at the back? Okay. Does that make sense? So I directly control z using u1, and I control y using phi. So now, how do I control phi? Well, for phi, I actually have an input u2. So I have the ability to control this moment, so I crank through this in a fairly standard way. So u2 is given by what phi needs to be. It's second derivative, and then I make u2 equal to this, and that drives phi exponentially to 0. So essentially, I have these three controllers, one for z, one for y, one for phi, and that's basically all these three controllers act in concert to drive the vehicle to the desired value. But this is only valid for small excursions about the hover position. And if you look at this architecture we have here, you'll see that the inner loop essentially controls the rotation and angular velocity. And so this is the phi control, and the outer loop essentially regulates the translation. Now, if I write it down in 6 dimensions, it's just a little more complicated, but the essence of the treatment is the same. I'm not going to spend too much time going over this, except now u1 is this scalar quantity, u2 is this vector quantity, and I go about it in exactly the same way. I linearize about the hover point, I write down the acceleration equations, and then I drive these exponentially convergent laws. If you understood the planar case, the spatial case is just a little bit more of math. That's all. Okay? And like I said, I promised to leave the slides, so if you're interested, you're welcome to take a look at this. Okay. So in our lab, students, so the class I teach has about 30 students. Every student essentially tries to write these controllers. Yes, please. Yes. Actually, I'll come to that. There's one thing this does not model, and that is the so-called ground effects. When you come close to the ground, the effective thrust that you generate increases, right? Because the air column below the robot is actually smaller. So you get more push-off this way. This particular controller will not do that. So when you try to land, it'll try hard to fight the ground and stay away from the ground. And actually the opposite is true. When you go to the ceiling effect, which we found out the hard way, actually pulls the robot into the ceiling. And you don't expect that. You don't expect something to actually suck the robot in. But the ceiling effect is one thing we found. The other thing we found is if you're going close to a wall, because of airflow close to the wall, and you might have seen it if you have two cars going really fast close to each other, you see the buffeting. And actually the cars are actually getting pulled into each other, or in trains, for example. And so that's another thing that this does not model. So in the lab, we actually run adaptive control loops to accommodate all of those things. If you go to our website, you can actually download dynamic models for this robot, a MATLAB simulator, controllers for these quadrotors, and fly the robot along planned trajectories. And I don't know if you saw this video or not, but let me replay it. So this video essentially shows the robot, and this is sort of our first exercise we give to the students. They figure out, first in simulation, how to hover, they tune gains, and then they essentially design these trajectories. And you can see this one is particularly good. There's very little, it's not jittery, the controller is very well tuned. But this is essentially what they have to do in the lab. And the nice thing is that these robots are really small. It's only 176 grams, and so they cannot hurt themselves. If you build smaller robots, one nice thing is your fingers are safer. So over the years, the number of Band-Aids we have to order has now gone down. So that's good. So the simulator also allows them to essentially get a sense of how to tune gains. Now these are, some of our students are computer scientists who have never had a controls class. So they come in, they have some sense of how the system actually behaves by looking at linear systems. So this is again at the z direction. And this is an example of a particularly good exercise by one of the students. And you can see, again, in the vertical direction, they are essentially using a controller similar to what I just showed you. And again, these videos are available online. Actually, the class I teach is called MEAM 620. So if you Google MEAM 620, University of Pennsylvania, you should find the website. And so again, examples of, so this one is you can see the settling time is quite significant. It takes a long time to settle. And this one is overdamped, right? And that's why you can see the settling time is large. I don't know what this one is. Let me play this again. This one's underdamped. You'll see a little bit of overshoot there. And then the last one is unstable. For obvious reasons, you won't have an experiment. But these are examples of what the students actually do as they figure out how to drive the robot. So I've only presented linear controllers. I'll come back to the nonlinear piece in a bit, but let me ask if there are any questions before I move forward. Questions? Yes.
Hi. Are the robots self-contained in terms of sensors and that kind of stuff? Or is there like cameras?
Good question. So here we use motion capture cameras. And until I come to the state estimation part, every experiment that you've seen thus far is being done on robots with reflective markers and motion capture cameras that provide state estimates. Here, the emphasis is on understanding the dynamics and learning how to control them. Any other questions? Okay. So let me talk a little bit about planning. I guess I won't. Which one is don't send?
Right.
Okay, good. And you're now looking at all my email. I know there's a better way of doing it. I cannot see that screen from here, so. Okay. So, in terms of planning trajectories, I want to remind you that the two sets of inputs we have are U1 and U2. So U1 is a scalar quantity. This is simply the net thrust coming from the rotors. U2 is the net moment. So if F1, F2, F3, F4 are the four thrusts, then multiply this by length and take into account the fact that some of the rotors are spinning with opposite pitch, and you get this equation, right? So these are the two inputs. Now, it turns out that there's a one-to-one correspondence between the state and inputs on the right side and these variables. So again, on the right side, you have the position, sorry, the state vector and its derivative. You also have the input U1, the derivative of the input U1 dot, its second derivative, and just U2. Okay? So I've constructed this vector in a clever way. Again, there are 6 of these, 6 more of those, so that's 12, 13, 14, 15, plus 3 of these, so that's 18. And on this side, I have position, velocity, acceleration, the derivative of acceleration, which is called jerk, the derivative of jerk, which is called snap, the yaw angle, the derivative of the yaw angle, and the second derivative of the yaw angle. So it turns out mathematically, you can relate these one-to-one. In other words, if I know this vector, I can find that. If I know this vector, I can find that. And the calculations are algebraic. I just show you some of the calculations. This is true except at one singularity. But for the most part, this vector and this vector are true, are the same. You know, if you compute this, you can compute that, and the other way around. The nice thing about this vector is there are no inputs. So this is simply a problem in geometry. But if I look at this vector, it's just the geometry of the space. If I take a curve in three-dimensional space, then that curve, when differentiated, will give me velocity, and then acceleration, then jerk and snap. Now, if I combine that curve with a heading angle, you differentiate the heading angle, you'll get psi dot and psi double dot. So this curve is a computational geometry representation of the motion. The curve on the right could be much more complicated. It has to do with dynamics and so on and so forth. But the nice thing is that because of this correspondence, I can ignore the dynamics and simply think about this in terms of geometry. So when I plan trajectories in the world, I simply plan in this space. So the key observation here is that all of these variables actually depend on the position and yaw. In fact, if I take this vector sigma consisting of x, which is x, y, and z, and yaw, it's a four-dimensional vector. All the other variables are derivatives of this four-dimensional vector. So this brings this idea of differential flatness that you can leverage. So again, the idea is that in general, you have all of these guys that you need to describe this robot with, which is a complicated space, a special Euclidean group in 3 dimensions, along with its derivatives. And rather than think about the dynamics of that, you can think about this nicer space, which is almost flat. So x, y, z is certainly the Euclidean space. There's no Euclidean geometry work, so that's a flat space. And this angle psi, which is the heading angle, is almost flat. Actually, technically, the heading angle is like a circle. But if you snip the circle and you stretch it out from 0 to 2 pi, it's also like the real line, or segment of the real line. So this is a flat space, and our calculation is essentially telling us that anything over here can be represented by a sufficiently smooth trajectory here. So if I find a trajectory that's 4 times differentiable on the left side, that corresponds to something meaningful that this robot can execute. So the strategy is, instead of thinking about curves in this complex space, you can think about curves in this flat space. So our goal is to come up with a trajectory in this flat space, a time parameterized trajectory that lives in the space of positions and yaw angles. That's the planning problem. So again, in this flat space, an obvious way to think about the trajectory is by minimizing this integral cost functional. So this cost functional depends on the position history and the yaw history. If I can minimize this, that'll essentially allow me to come up with smooth curves in this flat space. And once I come up with that, I can transform it into this more complex space and get realistic motions. And that's the key idea. Now, the details have to do with how you parameterize the position and the yaw. We use polynomial functions. And then how do you put in state and input constraints? So these are general nonlinear, but we essentially use linear approximations of these. And then finally, we reduce it to a quadratic program. Now, all the planning problems that we solve in the lab on the robots are essentially of this form. We solve this quadratic program, and we do it 20 times, 40 times a second, and that's how the robot figures out how to move in the 3-dimensional world. So once you have that, how do we do control? So now, the key observation for nonlinear control, as opposed to linear control, is that the angular error, so this is now a controller on the special orthogonal group in 3 dimensions. So the angular error, so suppose I want to be at r desired, a desired rotation matrix, and your current rotation is just r. So what's the error between one rotation and another rotation? Right? This is hard to intuit. If I tell you I have a position vector, another position vector, you can simply subtract them to find the error. But if I give you a 3 by 3 rotation matrix and another 3 by 3 rotation matrix, what's the error? Right? What's the difference? You cannot subtract them. In fact, the difference of 2 rotation matrices is not even a rotation matrix. But what you can do is do this computation where you take one rotation matrix, transpose it, multiply by the other, and you subtract that from the identity. Then you take the trace and divide that by 2. And magically, this quantity happens to be 1 minus the cosine of the angle between these two orientations. In other words, if I have one orientation here, another orientation here, there's a natural way of rotating, and that angle is this angle over here. So the cosine of this angle, 1 minus that, is essentially what you get by doing this complex operation. So what you'd like to do is not approximate this error by the angle, but instead use this approximation. Right? So if you use just the angle, you would essentially approximate this thing by a straight line like that, or a straight line like this. So we don't want to do that. We want to get the right angle. So that's the key high-level idea. So now imagine you have a trajectory that you've been prescribed. So I did this calculation, I solved this quadratic program, I did all this math and all this computation, I gave you a trajectory. Now you have to design a controller that follows the trajectory. How do I do that? So my first strategy is to ignore the fact that it's underactuated. So if it's not underactuated, what do I want to do? Well, I take the position, and essentially I do a proportional plus derivative control law, right? And I compensate for gravity. And I apply a thrust, which is essentially equal to, compensates for the error, and there's a feed-forward term that drives it in the direction I want to go. But what's wrong with this? The key thing that's wrong is that the resulting thrust can be in a random direction. It doesn't have to be in the z direction. So my robot is pointing this way, but I want to go that way. So what's the next best thing I can do? Well, I find the best possible way of generating that thrust. I take t, the direction I want the thrust to point. I take k, the direction in which the thrust can point, and I compute the magnitude by doing this dot product. Okay? So that's close to getting me to the actual thrust, provided that this angle is small. But there's another thing I can do. I can take this k, and I can try to reorient the robot so that this k is pointing in this direction. So that's the second piece. Knowing what direction I want to point in, which I can compute by saying E3 has to be along t, so this direction has to be along t, and that the orientation in the heading direction has to be the specified psi desired, I can compute r desired. And then I can compute my error, the way I described to you earlier. And then I can do a PD control law which depends on this error and its derivative. So this is the correct error and the derivative of that correct error. And then I compensate for inertia, I compensate for the nonlinear terms, and that's my moment. So that's the nonlinear controller. There's no linearization, and this works anywhere. If the robot is here, it's here, doesn't matter. And you can show that this controller converges, is globally asymptotically stable. So this is how you get F and M. And let me show you this short video clip by Daniel Mallinger that illustrates how the controller works. No matter how you throw the robot in the air, it's being asked to go to the hover position. And because it's a nonlinear controller, it's able to tolerate these very large excursions from the hover position. This tells you that the basin of attraction is almost all of SO3. So the only way you reach this boundary is if R and R desired are exactly opposite. So if R is over here, R desired is over here, that's when this inequality fails. Sorry. Going backwards. There we go. That's when this fails. Another thing you'll notice is that this term on the right tells you what your angular velocities can be, how much error you can tolerate. So it turns out you can tolerate a lot of error, and if you make your inertia small, then the amount of error you can tolerate is even more. So if your robots are smaller, your basin of attraction increases and your controller is more robust. And so this is the key idea. We again find the minimum snap trajectory. So again, you're minimizing the snap of the trajectory. We make sure that we avoid obstacles, and then we translate that into the actual manifold, and that's essentially what we feed the robot. Now, in our architecture, some of this is done on board. The nonlinear controller is essentially running on board, but the feedback of the positions come from motion capture cameras, and the actual quadratic program that's being solved for the trajectories is being done on the robot. So essentially, this is like cloud computing. There's a computer on board that's doing this low-level computation. There's another computer on board that's figuring out where the robots are and telling the robots where they are. And then there's a third computer that's telling the robots how to move. And they're all sort of all this is happening in real time at rates from 1 millisecond down to about 10 hertz, tenth of a second. So this is what a minimum snap trajectory looks like, again, going from A to B through this intermediate point C. The interesting thing about this trajectory is you have to remember that the planning is done in this flat space. So essentially what the instructions are is to start from here, go to that point, and go there. And here's a smooth trajectory in XYZ space. But because of this mapping, that smooth trajectory in the flat space gets translated into this very complex trajectory into the real space, which involves these very high roll and pitch angles. But we're not explicitly calculating them. And then lastly, if you know there are obstacles in the environment, it's actually quite easy to say, well, I want my smooth trajectory in this flat space to avoid obstacles. And then when that is translated into the real world, you get these fairly complex trajectories. And again, it doesn't matter if these obstacles are actually moving, because the robot can essentially see where the obstacles are. And now your constraints become time varying, but it can plot a smooth curve through that, and then that is fed forward as part of the plan. Again, everything here is being done with the motion capture cameras for position feedback. Any questions? Yes, so in this picture, the obstacles are stationary. Whether they're stationary or not, they actually have little markers here. You cannot see them, so the robot knows where they are. And when it's falling, you can actually extrapolate the motion in between the frames. So remember, the feedback is coming at 1/100th of a second. And in between, you know, because of Newton's laws, how fast the thing is falling. So the constraint becomes a time-varying constraint. Any other questions? Yes?
Professor, with the first model that you did with the control of PC, yaw, raw, and pitch, and X, Z, I thought the control would work with a polynomial equation to go to a waypoint to another, but after you did another planning with optimization to plan the trajectory. My question is, it would work if I only did a polynomial equation from this waypoint to that, with X, Y, and Z?
So I'm not sure exactly I understand your question, but let me try to answer it anyway. Right? So let's say you have waypoints that you have to go through. One way of doing it is to try to fit a polynomial through all those waypoints. If you do that, then the order of the polynomial will be very high, and it'll have lots of bends. And if you do that, the resulting trajectory in the real world will violate all your state constraints. So things like, so one of the constraints we have is you're not allowed to turn faster than so much. I think it's 240 degrees per second, because that's when the gyros saturate. So because of that, what we do is we take separate polynomials and we join them at the waypoints. So that way the order is constant. Okay?
How do you communicate with the robot?
So we use two radios. One is Wi-Fi and one is Zigbee radios. So Zigbee radios are either 2.4 gigahertz or 900 megahertz. Yeah, so everything is off the shelf. Nothing new here. And because of that, communication is always a problem. If I go in with this wireless microphone, that interferes. If somebody has a cordless phone, I don't know if people use cordless phones anymore, but we have one cordless phone which we now don't have anymore because of the interference. There's one other question. Yes?
How far you can access, you can communicate for each robot?
This is a fairly small lab, so the communication is not, there are all kinds of problems with communication, but it's not because of range. It's because of the noise in the environment, because 2.4 gigahertz is a very commonly used frequency. Okay. The other thing so these are some extensions. Our robots don't manipulate, but we'd love to see them manipulate, like the eagle here is fishing for salmon. So here's our robot. So it turns out this differential flatness formulation, the optimal control approach, the incorporation of state constraints, the motion capture camera system, all of that generalizes nicely to simple tasks where you can actually swing this thing back and pick it up. And again, I don't know if you noticed or not, both in the case of the eagle and in the case, so look at what the eyes are pointing down, and when it picks up the fish, the relative velocity is 0. So the feet are swinging back as it's ready to grasp that. And the exact same thing with this robot. It's going at 2 meters per second. I think next one's at 3 meters per second. And you'll see that the key thing is to synchronize the flying motion and the reaching motion so that you don't miss the object. Yes?
Is it possible to do that without with a fixed manipulator? Like manipulator has no degrees of freedom.
It's hard to do it without that, because if you're going really fast, you're going to hit the object. So then you have to have a gripper that actually sucks it in when it goes, and that's hard to do. So if you look at birds, so this is an eagle. We've studied raptors. They always, when they grab prey, they have to go fast, otherwise the prey will run away. And they compensate for that by moving their arms back to grab it. So, and there are other things you can do. So for flying through windows, for example, we use a combination of controllers. So there's a hover controller where you start from. Then we use the controller I just described in the planner to build up momentum. But over here, you don't care about position. All you're caring about is orientation. So let's look at it again. So it's going to take off, and right around this point, it's going to switch to just an attitude controller, where it switches to a different controller and then switches back into another controller. So you can play games like this by doing piecewise stitching of these controllers for more complex maneuvers. So let me move into another chapter, which has to do with sensing. So as you all notice, that everything in this lab is being done with these motion capture cameras and with these reflective markers. And I just talked about search and rescue, first response. Well, I cannot tell the policeman to wait. Let me set up a motion capture camera, and then my robot will go in. So you can't do that, right? So state estimation is a big challenge, particularly for small vehicles, and particularly indoors. In big vehicles like this, this is the X47B, which Northrop Grumman makes. Of course you have GPS. You have amazing communications. And that's how they do landing on ship decks autonomously. This is our lab, live-in hall. If you're outside this hall, I guarantee you will not be able to get GPS in the shadow of this building. And certainly indoors, there's no GPS. So the question is, how can we get robots to essentially localize themselves? And this was one of our first attempts to do this. This robot's about 3 years old. It has on it, again, an off-the-shelf camera, Microsoft Kinect, the Xbox camera, which is a color plus depth camera, and a laser scanner that essentially has a 30-meter range. It's a planar scanner, so it shoots out a laser beam through a scanning mirror, and it gets reflections from points that are at most 30 meters away. So it can build a planar depth map as it flies. This is something a little more complicated. It has not only the laser scanner, but it also has a stereo camera. It also has GPS, also has a downward-facing camera looking down to infer how quickly it's traveling. In all of these robots, the robot essentially uses what is called a simultaneous localization and mapping algorithm in order to determine where it is. So I'm not going to give you a lecture on SLAM, as it's called, but let me try to give you the sense of this by using a very simple picture. So the idea here is that the robot is over here. Now imagine there are features that can be seen by the robot. Now these features could be pillars, right? Or they could be features that a camera detects. So you can have feature detectors running on camera images, and those features might not look like anything rational to you and me, but a camera and a processor will find those features reliably. So there are these features in the environment. The robot starts off here. It doesn't know where the features are. It does not know where it is. So when it starts off at position 0, it may be that it sees 3 features. Right? So each of these features now tell the robot where it is relative to those features. When it goes to a new position, it might find 2 other features. When it goes to another position, it might find only 1 feature, and so on and so forth. Here it's found 4 features. So what you see here is a graph. And the graph has 2 types of edges. Right? The first kind of an edge is the edge that basically tells you what measurements are being made from what point. So each of these z variables may represent a vision measurement or a depth measurement by a laser. But each of those edges represents a measurement which is potentially noisy, but does give you some idea of where the x is relative to the f's. And then there are these other edges, and those edges have to do with dynamics. So if I take 1 step, my brain registers the fact that I've taken a step, and I have a rough idea where I am. So that's this arrow. So this is basically telling me that x1 is some function of where I started off and what input I applied, the number of steps, or in the robot's case, how much thrust I applied in each propeller, and for how long. And that's these edges. So now you have a graph where you have lots of edges. Each edge represents an equation or perhaps many equations. So now I'm going to tell you, solve this optimization problem. Right? And I'm going to tell you it's possible to do it. Right? So it's not immediately obvious that this optimization problem is well posed. But if you look at this, it's a nonlinear optimization problem. And there are lots of open source toolboxes that allow you now to solve these SLAM problems. If you can do that, then you will know what x1 is relative to x0, where x2 is relative to x0, where x3 is relative to x0. You also know where these features are in the real world. So that's the key idea in a SLAM problem. So to see this operating, I want to show you, well, first I'll show you some of the sensors we use. So, and this is mostly to show you what these edges look like. So an IMU is perhaps the most important sensor. At 100 hertz, it's going to tell you where I am relative to where I was based on what input I provided with some noise. Then there are, when we're lucky, we have GPS, a magnetometer, a compass that tells you the heading direction, an altimeter that tells you the vertical height. So you have observations. There are some functions of x, the state, with some noise. But the most important sensors are relative sensors. So these are, in some sense, absolute sensors. They're telling you where x is, and maybe a nonlinear function, but still telling you what the state is. These relative sensors, on the other hand, tell you something about where xt is relative to xt minus 1, xt minus 2, and so on and so forth. So the laser scanners and cameras are exactly that. They don't give you absolute position. They only give you relative position. So this is a filter then that tries to pull all of these things together. So let me walk you through this filter. Again, our bottom line is we want to use that trajectory generator I showed you and the planner I showed you and this controller. Our controller runs at 100 hertz, which means we need estimates coming at 100 hertz without motion capture cameras. So we have here a filter, which is essentially an unscented common filter. And I'm not going to talk about that, but if you want, I can talk about it tomorrow if there's some interest, which combines information from the GPS, from laser scanner, pressure altimeter, stereo camera, the downward-facing camera, and the IMU. All of this thing goes in through various threads, and these are all coming in at different rates, 10 hertz, 20 hertz, 25 hertz, 30 hertz, 100 hertz. This runs at 100 hertz, and that feeds the controller. So this is key to making everything work. Now, the output of this also goes into the SLAM algorithm, and that's what creates the map. And that map is important because without that map, I cannot really estimate where I am in the environment, and it's used for laser odometry, for instance, and it's also used for attitude estimation. Okay? So here's a very simple example. This is work by Xiaoji Shen, who's now at the assistant professor at Hong Kong University of Science and Technology. This robot with a single laser scanner essentially entering into the building, and it tells you what kind of map we can build. So this is that SLAM algorithm working. This is what he sees when he's operating the robot. The robot goes into the building, he's outside, and he's essentially telling this robot where to go by looking at this map. So every little red segment that you see is something that's planned by the robot. So you'll see this video again. He's clicking at points he wants the robot to go to. So there's the first click, the robot goes there. You'll see him clicking again, and the robot plans its path to that. When the robot goes there, it gathers more information, thereby increasing the quality of the map. And that information is fed back to the operator, allowing him to direct it in more interesting ways. All this information is aggregated, and the main goal here is to build a map of a building without entering it. And this is a multi-storied map. The blue is essentially the ground floor, and as you go to colors that are hotter and hotter, those colors are essentially representing higher level floors. It's a four-storied building. So without motion capture cameras, you can do roughly what we did in the lab, except it has to be a lot slower. The estimates are about, in terms of statistically, the standard deviations are about twice what you get with a motion capture camera. The environments are a lot more cluttered, and so the speeds are a lot slower. So in the lab, we can do 5-6 meters per second. Here, we don't exceed 2 meters per second. Another thing we can do is also tell the robot to determine where it needs to go. So here, all of these blobs that show up, so these blobs are automatically identified by the robot as points at which the robot thinks it can get more information. So it determines, instead of the human, what waypoints to go to. And this way, the robot can essentially enter the building without the human clicking on points. So imagine you had, for instance, the need to go into a reactor building which is contaminated. The robot goes in. The first thing that fails when you have radioactive contamination is your wireless link, right? So there's no way for me to click on waypoints. But this way, the robot can actually go explore the building and then come close to an area where I can actually retrieve the information. So you need these kinds of autonomous exploration algorithms for robots like this to be practical. Yes? So the question is, what kind of a model do we use for SLAM? So here, I told you that in our graph, we're actually using a model which tells you where we're going to based on our current state. In everything that I've shown you, the robot essentially uses IMU information. So the IMU is essentially a good indicator of how fast you're accelerating and how much you're trying to turn. And it's more reliable than taking noisy velocity measurements. Actually, in our smaller robots, it's actually hard even for the robot to get measurements. We don't have a propeller, a sensor, a tachometer on each of the propellers. So we don't even know. We're commanding a particular velocity, but we don't know what velocity we're getting. So we just take the IMU information here. Yes?
What techniques are you using for the autonomous exploration? How do you select the waypoints?
Great question. So we have several different algorithms. In this particular one, we're essentially looking for the point at which we get maximum exposure to unexplored spaces. So this is not frontier-based. The problem with frontier-based algorithms is that in 3 dimensions, they don't scale well. It's hard to detect frontiers. So in this particular case, the robot essentially does a crazy thing. It simulates a gaseous cloud. And if you imagine a gas being released here, it's going to go to open spaces. So it represents this gas through a stochastic differential equation using a few particles to simulate the continuum. We're not interested in the accuracy of the simulation. What we're interested in is actually finding these open spaces, and that's how we explore. Okay, I'm going to take maybe 5 minutes and tell you about, is that good, Guilherme? Okay. To tell you about the big picture, why it's hard to build these robots in small packages. First of all, size matters, right? And the reason it matters is because the laws of physics change depending, or they don't change, but they dramatically influence the performance based on size. So let's take this variable r, and you look at how masses, inertias, thrusts, etc. change as you change r. So it turns out, the first thing that you can see is that as you make things smaller, you become more agile. So here's one of our smallest robots. It's about 70 grams, and it can perform flips in less than half a second, which means it's going up to all the way up and turning around in about a quarter of a second and reaching speeds of about 2,000 degrees per second. So the acceleration you can get out of these small vehicles is incredible. So it's intuitively obvious. The second thing is the smaller vehicles take less power. So this vehicle is the smallest one we've built. It's only 11 centimeters tip to tip, and it consumes only 6.5 watts, right? So that's really small compared to the robots I showed you with the laser scanners and so on, which consume about 400 to 500 watts. So that's half a kilowatt of power. That's a lot of power. And if you look at the smallest robots we have, again, we design it so that there's very little stuff that they have to carry on board. In fact, everything here is modular. We put all the electronics in the central hub. We put the motor drivers on these arms. And there's only enough room for inertial sensors, for radios, and for one camera and for batteries. So something like this, you can probably get up and running with minimal payload. And minimal payload means minimal power. And minimal power means you can last longer. At least that's the theory. So this one, for example, 2 kilos consumes about 400 watts. So power is a problem, right? If you have a cell phone, you have a laptop, you know this. But let me try to quantify this for you, how bad it is. So you can look at power in terms of energy divided by unit mass, or power divided by unit mass. So this is specific power, this is specific energy. So this is the lithium polymer batteries you can buy today. So there are two pieces to the bad news, right? The first piece of the bad news is obvious. There's nothing on this side, which means you can't operate for a long time. But you know that from carrying cell phones and laptops. But how bad is it? Well, this is a piece of fat. I mean, I might look thin, but I also carry fat, right? So this is 10,000 watt-hours per kilo. The best batteries do maybe 200 watt-hours per kilo. So we are much, much better than lithium polymer batteries. The second one is actually our inability to make efficient flying vehicles. So this is not because I'm a bad designer. This is because of physics. Quad rotors essentially consume roughly 200 watts per kilo. And again, this is bad because you're burning a lot of power and you're not carrying a lot of energy. And again, comparing this to human beings, I can compare it to the most inefficient person on Earth, I claim, who also happens to be the fastest man on Earth, Usain Bolt. So in a 10-second dash, he burns about 20 watts per kilo. I guarantee you, I don't know, if there are athletes here, but you're not close to 20 watts per kilo, right? When I'm running full speed on a treadmill, I do maybe 3 watts per kilo. Another person you can compare it to is Lance Armstrong. I know he's had steroids and all that, but the amount of power output is the same. With steroids, without steroids, this is a mechanical thing. So he's about 6 watts per kilo, and this is in longer stints. So to get to, these are really inefficient people because they want to win races. Our robots are much, much more inefficient, and there's no way around that. So what's the solution? Notice that both of these are divided by weight. So the best thing we can do is lose weight. Just like the doctor tells many of us, that's our solution for robots as well. You lose weight. And we've built many robots, and we've tried to scale this down. And one of the things you also can see is if you scale the length down, it turns out that the tip speed of the blades, given by the Mach number, also comes down. And there's an interesting scaling law. Actually, the velocity goes as the square of the length, the square root of the length. This, by the way, is the same scaling law we encounter in nature. If I take a short person in this room and a tall person in the room, and if I measure the stride length, chances are our walking speed goes roughly as the square root of the length of the leg. And this is true for our robots as well. But because of that, we can show through the equations of motion and the aerodynamics that the turning acceleration goes as 1 over L. In other words, if I take a robot and make it half its size, it's going to accelerate twice as fast. So you get agility because of these scaling laws. And I'm going to skip all of this because it's late in the day, but trust me, this all works. And so this paradigm of Froude scaling, essentially, we've shown is sort of invariant across all of these robots. Some of these are off the shelf. Somebody asked about Aztec hummingbirds. This is off the shelf. This is also off the shelf. And these are things that we've made ourselves, this with our spin